So let me start. Then I will go on the note, but let me put a name. Name equals 197 in topic course and regime. So what is rigidity? We will see in a second. Now let me take 2 minutes because the computer finally is on. So let me see how it works. So what does it mean rigidity? Okay, so that's the main question of the course, and that's what we are going to address. And there is not a universal definition of rigidity. So my hope is that by the end of the course, it's clear for everyone what are we talking about rigidity. So I will give you some examples of rigidity. I will wave my hand trying to explain you what we want to think about a rigid thing or a non-rigid thing. And as I said, there is no clear definition, although the name and the word itself should tell you quite a bit of what should be the meaning of this word rigidity and what we care about rigidity in mathematics. So there are in most areas of mathematics, you have then some rigidity phenomena, and mostly we will care here about Lie groups, lattices, geometry, and with a very dynamical perspective. So the very basic we need to understand what's happening in the course will be measure theory. So we really need to have to play quite a bit with measure theory. Linear algebra, a lot. Calculus, of course. If you know ergodic theory, it's a big plus. If not, we still will be developing it and you will have to read a little bit. Basics of dynamics, whatever you have is for the better. Lie group theory, if you know it, it makes a lot of concepts we are going to discuss much simpler. In any event, I plan to do things in the simpler situations, so just linear algebra will do. And actually, if you try to go further, then there are subtle complications because Lie groups are not all the same. But in the simpler situation, things can be described very easily and we don't need to worry that much. That's pretty much what we need. Okay, so I will not follow any book. So there is no book that will contain whatever we are going to, so all we are going to discuss, at least not the type of approach I plan to follow. So I still will give you references as times come where whatever statement I'm talking about can be seen, find the proof of it. Not most likely not the proof we are going to talk about or the type of approach, but still it is a proof. So a lot of things here in this course has to do with the approach we are choosing to these problems. Okay, so there are several approaches by different people, more geometric, more measure theoretic, more C-star algebra. We are doing here a more dynamical system approach to the theory. Okay, so let me try again. Okay, forget about it. So these computers don't even have the Zoom installed, so probably from when I was young. So let's just go today with that and we will see what happens in the future. So let me start with one example of a rigid phenomenon, a very simple example. We will prove it all together, and then I will start trying to explain why I would like to think of this as a very rigid phenomenon. a very simple lemma. I like it a lot. It says let L from R to R here with addition group. Be a homomorphism. We have a homomorphism of the group. You know several of these examples. You have the zero function, you have the identity, you have multiplication by whatever number you want, 2x, typical. Now the question is, are there more than them? And the answer, or one answer here is the following, which is, we have this homomorphism, then L is linear, and this means there exists a R such that L of x for every x, so it's multiplication by a number, if and only if L is Borel measurable. Okay, so let's see. Can you see what I wrote? Yes, I guess I can see, so you can. Okay, so what's Borel measurable? Means preimage of Borel set is Borel. What's the Borel algebra here? Borel sigma algebra is the sigma generated by compact set or open sets or closed sets. This is the real, so it's really no surprise there. Standard topology, standard everything, addition. So there are plenty of Borel measurable maps. Being Borel measurable is a very weak notion. Okay? And here the importance is to understand how weak is this notion of Borel measurable. And part of the game here is this source of rigidity coming from such a weak notion and such a smooth, in a sense, notion, not smooth because of smooth functions, but smooth because you can play with it a lot. So it's very soft. So before we go to do the proof of this altogether, as you may know, and I hope you know, if not, you can just Google it. All this, most what I'm going to talk always is in Wikipedia, so you can always Wikipedia it. Every measurable space, every Borel measurable space, under very mild assumptions, is essentially the interval 0, 1, or the real lines from the Borel perspective. So you may have some atoms, so you have separating points, countably many points at most. You need some second countable type of some numberability or countability conditions to guarantee that, but that's it. So which means that from the measure perspective, there is only the interval 0, 1, or the reals with plus countably many points. But on the other hand, you have a sphere, a round sphere, with the constant curvature 1 metric, is a very rigid object. So you cannot deform it at all. So you can do nothing with it. It's really round. So if you want to think more topologically, then you can bump it and do a lot of things, twist it a little bit, and still will be a sphere, okay, and nothing else. So you cannot break it, because then it stops being a sphere. Now, from the geometry point of view, if it is not round, it's not the round sphere. Okay. Now, this softness of any Borel space, under this very mild assumption that we always assume, being just the interval 0, 1, plus countably many points, you can even think of this as also a rigidity statement. Even though I don't want you to think of it, but if you want, you can push as well and say it's rigidity, because what you are saying is you can try to do whatever you want with a Borel space. You will never be able to break this fact of being the interval 0, 1 and find countably many points. So you can try to twist it and do whatever in a measurable manner. And at the end of the day, you still have the interval 0, 1. So then comes the game of rigidity. So it's what type of deformations am I allowing and what the type of rigidity I am getting. Okay, and in which class of spaces I am moving. So one very important instance of rigidity is the famous Mostow rigidity theorem. We will not start with it. I hope we will reach it at some point later in the course, which says, okay, if I move only among, maybe before it, okay, no, let me state it. So if I move along three-dimensional manifold with metrics of curvature -1, and I take one such compact manifold, and I try to make a deformation of it. Okay, so I try to move it, do something about it, but keeping the curvature constant -1. And the question is, can I do it? And the first answer, and this is fairly simple in a sense, because I'm talking about deformation, so you will be see what I'm doing here. And the answer is no. You cannot make any deformation. So it will still be the very same isometric manifold as before. Now, what about if I'm a better magician and I just promise you that I will not change the topological structure, but I will turn around, do my trick here, and bring it back. So then you don't know whether I broke the pieces and glue them in a different form or do some strange operation. Back there, I just guarantee that topologically is the same. Let's say homeomorphic first. And then the answer is still they are isometric. That's Mostow rigidity. And even Mostow goes one step further and tells you that even if they are not homeomorphic, just same fundamental group, they still will be isometric. So really, you cannot change. So as soon as you keep the topological, the very coarse topological structure, and want also to be constant -1 curvature, then you will have the same object. The same as happens with the round sphere. Okay? Now this is in dimension 3. If you try to do the same in dimension 2, then it's not true. It's what gives rise to the whole Teichmuller theory. So you have a finite dimensional space of deformations. So I can take a genus 2 torus, and I can do the same as what we are discussing, and I can have it with constant curvature -1, and I can start deforming it. The simplest one will be, let's say, of course, I cannot do it in R3 because constant curvature -1 is not fitting in R3, but in any event, one very easy deformation you can do is you have this genus 2 torus, so the two handles here, so 2 tori minus a disk glued together, and then I have first both them horizontal, and then I just rotate this guy. And by making this rotation, this will not be isometric anymore. You can just play a little bit with angles and you will see that they cannot be isometric anymore. And still the curvature will not change if I do it correctly. Okay, so curvature will still be -1 and it's still a genus 2 torus. And you can do other things. I could shrink the length of this geodesic here, and then you can see that certainly maybe even simpler to check that they are not isometric because the length of this geodesic should remain, at least if the isometry were close to the identity, the standard guide, and still keep curvature -1. So, and this gives rise to Teichmuller theory. You can parameterize all this deformation and parameterize Teichmuller space, and there is a huge theory on it. Now, this is lack of rigidity, even though there is still some rigidity if you want, because after all, it's just finite dimensional space of deformation. So this still gives you some control on what's going on in the world. But certainly for dimension 3 and higher, for these hyperbolic manifolds, you have the stronger rigidity. There is no deformation whatsoever. So It's no continuous deformation, no just jumping somewhere else and finding a space homotopic equivalent. There is nothing you can do. Now, there is a stronger rigidity statements when instead of working in curvature -1, you go to other type of homogeneous spaces which has flats. So a flat is an embedding of Rn or the torus Tn or corresponding cylinder in your manifolds. And assuming that to every point you have such a flat, you still will have this Mostow type of rigidity and even more stronger rigidity statements. Now, the approach we will do to this, even though I spoke everything very geometrically, is putting first some group theory behind what we are talking here, and then we will be talking about homomorphisms instead of isometries, or homomorphism, or topological or homotopic equivalencies. And eventually the problem, the group theoretic problem, we will translate it to a dynamical problem, and we will solve the dynamical problem. The dynamical problem will solve the group theoretic problem, and the group theoretic problem will solve the geometric problem. Okay, so this is the group theoretic problem here. So here what I'm saying is I have this homomorphism, and I know just it's measurable. Then I can give a full description of what it is. Okay, so let's first give an example of a non-measurable homomorphism to see that this fails. For the other guys, that's easy, I hope. R is the Q vector space. And when you look for homomorphism with the addition, you only care about R being a Q vector space. And any Q linear map are in one-to-one correspondence with homomorphism. Once you have this, you take, well, you have to work a little bit. You just need to make sure you have two rational independent guys, so that these two guys are linearly independent of the rationals. So that's crucial. Once I can build T from R to R, the T of 1 equal to 1, and T of square root of 2 equal to 0, and then extend it. This way I build a homomorphism which maps 1 to 1, so it has to be identity if it were linear, but it sends square root of 2 to 0, so it cannot be linear. Okay? Now, why this guy is not measurable? Well, if you use the lemma, you will get in 2 seconds. Simple proof that it's not linear. If you remember how is this Vitali construction, is Vitali, no? I think it's Vitali. A construction of non-measurable set is pretty much this game. Okay. Now, I will prove this lemma for the reals. Still the same proof will work as soon as you have any groups. You want G1 locally compact. All groups we are going to work are locally compact. It's not really needed, but I want always to be second countable. I don't want to work with any monsters. I want it to be Hausdorff. So all the groups I'm going to work will be of this type. Mostly will be Lie groups. Maybe at some point some strange examples pop up. We will treat them. That's too small. Yes. Good. G1, locally compact. authors. And that's pretty much, eventually they will be just Lie groups always, but so far that's the basic assumptions we want of the groups. G2, you don't need locally compactness, but let's say it's still also locally compact. And then you will not have linear, you just remove this by continuous. But once it is continuous, it will be linear. And if you are in a Lie group, any continuous homomorphism is automatically smooth in the Lie group. So this is continuous. Okay. So let's try to build a proof of this. So first thing to think about is whenever you have a locally compact group, you have to think on Haar measure. So that's the magic of locally compact groups, that they have a Haar measure. So what is a Haar measure? Is a measure on this group which is invariant by left translation or right translation, depending on what you want to choose. Let's say left translation for our business. A Haar measure is lambda GA is lambda A for every G is left invariant or left invariant for every A. Okay, in our case of the reals, which is what we really focus, is just dt, is the length measure. So in the reals, we have a normalization, which is interval 0, 1 has measure 1. In general, you don't have any specific normalization unless you want something else, which you do sometimes. And it's a whole theory of computing volumes and doing a lot of things. This comes with this type of normalization. We will not enter into that, but this is also very much related with rigidity questions. Okay, but anyway, we will not go into there, at least not now, for sure. So we have this dt measure, and since even though the measure does not appear in the assumption, it still appears the notion of measurable sets. So using a measure is some handy thing. We have this Haar measure. This dt. So that will be the tool we will play with, the measure. Now, as I remarked there, so what you have to prove is continuity. We know that for linear, for homomorphism, you need just to care about continuity at 0. So you don't need to care about continuity at any other point. So the question is how to gain continuity at 0. And that's the question. So I only know that it's Borel measurable, and I want it to be continuous at 0. And actually continuous at any point, because if I can guarantee continuous at maybe 35, then still I get full continuity. So I need to find one point of continuity. Okay, but Borel measures, Borel measurable functions have no reason to be continuous at all. But what do you know about continuity for Borel measurable functions?
So you can use something like a Lucin theorem type thing?
Yes, you can certainly use Lucin. We are going to use Lucin. So you have restrictions which are continuous. And that's good. Because this gives me some baby source of continuity. And that's the game we will be doing here all the time. So you start gaining a little bit, keep on gaining a little bit, at least at the end, you gain all you want. Okay, so you have to get something where to start. So the first step is for a measurable implies there exists a set A that L lambda of A is positive, L restricted to A is continuous. Not false, this is L. Okay, so, but this is just the restriction. So, as soon as I move inside A, I'm good. If I move outside of A, I'm in trouble. Now, what we discuss is that we can move A freely. So, any translate, if I restrict to any translate of A, I will still have continuity. Yet, I need to keep being restricting there. So, when I take a sequence, let's say xn going to 0, if I can manage to make xn belong to A all the time, I'm good. And I'm allowed to translate A. But keeping A inside, the sequence inside A even translating, is not an easy task. I don't think you can do it actually. For a fixed translate. So we have to do some epsilon more of work. And certainly the fact that the L is linear should make the game. Okay, so let me maybe give you the magic. After all, I'm here to give you the magic happening. So what does the magic is, unless any of you know the magic, and then you can just say it by yourself. What's the next step? I can follow. If not, I do the magic trick. Okay, let's do it. If you don't want to spoil my trick, then I do. So A minus A contains the neighborhood of 0. That's the game. So we know that if you have a set of positive Haar measure, then the difference set contains a neighborhood of 0. And then the linearity will go from continuity in A to continuity in A minus A. And then I have continuity in a neighborhood of 0. That's all I need. So that's the magic. Okay, that's why linear maps are so strong. And part of the game is that what we are going to get in all this rigidity business are linear maps, homomorphisms. So they will start being some measurable strange map, and we will upgrade them to make them homomorphism. And this homomorphism will eventually will become isometries when you care about the geometry. So that's the game. So now you take xn going to 0, decompose this as yn minus en in A. We can assume A is compact because it's Lebesgue measure. So even if it is very large, I restrict to a compact set. Then I have yn and Cn belonging to A. I take any subsequence L of x and I. It could be divergent. If it were not divergent, it's very easy. It could be divergent, but I don't need to rule out the divergent, but this is L of y and I minus C and I can take subsequence of these guys, subsequence of the subsequence, any subsequence, and this will go to 0. L of y. Okay, I'm taking the subsequence of this guy converts to y, And it has to be L of y minus z. It's 0 because y minus z. Okay, I guess something I'm saying is probably wrong. You have to adjust it, but it's not very hard. Okay, maybe you have to be more careful with these compact sets and this taking subsequence. I leave it to you as an exercise. Okay, so but that's the magic. That's the game. So that's it. I think for me it's the nicest example of rigidity, where you start from nothing, you get linear. So let me use the rest of the day to give a description of SLNR and the properties of SLNR we really will care, and this will be our favorite Lie group. So we're working all the time with SLNR. This is N by N matrices, real entries, determinant one. Sometimes it is useful to think of this as automorphism of n-dimensional vector space, in which case, when ideally want to think of vector spaces, which sometimes is very useful, I just will use this type of notation. SLV, where V is the vector space, and we don't. So if it is not finite dimensional, then it's a pain, but when I use this notation, I'm thinking of finite dimensional vector spaces. And whether the vector space is over the reals or the complex or even the rationals, it will be understood from this notation. I will try to make clear which are the number field we are working. Most of the time will be R. Sometimes it could be the complex, sometimes it could be rational. We will never go to p-adic, it will be really way beyond, but one can do it as well. It is useful, the fact that this is a subgroup of GL, which is just remove the conditional terminal 1. So SL is what is called a simple Lie group. Simplicity is a very important property. We will use it and even semi-simplicity, but we will discuss it when times come. I said that I will not do p-adics, even though most of the proofs we are going to discuss with the appropriate change, which shouldn't be too much, will apply to p-adic. Okay? So really we can do make the theorems to work in p-adic, and this is very important for a lot of arithmetic questions. So SLNR as any simple group, and even semi-simple, has this KEM decomposition. That's also known as the Iwasawa decomposition, if I'm not mistaken, and it's nothing but this Gram-Schmidt orthogonalization method. Okay? So this K stands for SO R. This A stands for diagonal, but not just diagonal, it's diagonal with positive entries. So, because the negative entries can be taken to SO, and I want the composition to be unique. And I have N, these upper triangular matrices, with ones. Okay, so that's the main decomposition. And as I said, this is Gram-Schmidt method. We tell you that give you any basis, I can do a process inductively, which in each step I'm being the space generated is the same as the one I had. So here the basis is the columns of the matrix, or maybe the rows, I think the columns of the matrix. At each step, I'm having this upper triangular modification, which is what is guaranteeing that you get the same vector spaces at each step, and the outcome is an orthonormal basis, which is the matrix K. That's pretty much a way of stating Gram-Schmidt. This is true for any semi-simply group, even any simply group, but the proof is Gram-Schmidt orthogonalization method. Okay, so it's not nothing more complicated than that. Now, each of these guys is a Lie group. This guy is isomorphic to Rn minus 1. This is compact. That's why you have K. And these is nilpotent and is formed by upper triangle. Maybe I should have okay. We will see later. Okay, let me do some very simple linear algebra. And this very simple linear algebra already has a lot of dynamics inside of it. And in the course of the course, we are going to really see why this is a lot of dynamics. I take a matrix in A, and I multiply it by a very special matrix in N. Oops, it has an S entry in the I, J position. Fine. And then I multiply this by the inverse of this matrix. So the inverse of this matrix is very easy, equal minus P1, equal minus P2. So what do I do? When you go and do your computations, you will get still an upper triangular matrix with all ones in the diagonal. We have zeros everywhere outside from the ij position. And in the ij position, you will have S as before, but this S comes multiplied by e to the di minus tj. Or tj minus ti, let's check. So I do the I line, it goes with this I guy. I think I'm right, but I may be wrong. But I have 10 persons to check what I'm saying is correct. Is this Ta minus Tj or Tj minus Ta? When I multiply these three matrices.
So are you conjugating or?
I'm conjugating by the diagonal.
Okay.
So I'm multiplying the row, the I row, first row is nothing until I get the I row with the I column. And then I get something, I get the TI. And when I go the other way around, I go the J row with the J column, and I get something. If not, I get nothing. I'm right. I'm Ti minus Tj. Okay, so I'm 90% sure. It's not good enough for a theorem, but it's probably good enough to continue the course. So that's what I do. So I conjugate this matrix here by this diagonal A, and what I get is this entry multiplied by Ti minus Tj. So, and observe that this tells me two very important things. One is that this subgroup, which is the guys with this S in the ij position, right, the subgroup, all these matrices, identity plus S Aij, Haar, let's call it J, and Ij, this matrix, everything is 0, but the one here in the Ji position, everything is 0. This is a subgroup, and when I conjugate by this diagonal matrix, I get the same group, and not only get the same group, each element is multiplied by this number. Okay, so this is very important because it's telling me a way of thinking multiplication of matrices. Okay, and a way of thinking conjugating by a matrix. So it's not for any pair of matrices, how I multiply any pair of matrices, neither how I conjugate any pair of matrices. It's talking about this very specific pair of matrices. Still, this is very important because this is the building block for what we are going to do later. Okay, so it will be very important for us as well when we take the whole N guy. Here is already J. J. Not just one entry, it's all entries possible there. Here just fix one, all the others are 0. For example, we can do the very same computation and it will be no difference in the computation if we conjugate all the n, all the elements in n by element in D. Okay, so simply any upper triangular entry gets multiplied by this e to the Ti minus Tj. And actually that's what does conjugating by diagonal matrices. So every entry is multiplied by e to the Ti minus Tj. Okay, so the diagonal entries are not multiplied by nothing because Ti minus Ti is 0. The guys above give Ti minus Tj, the guy below is also Ti minus Tj, but it's symmetric or anti-symmetric. Okay, so conjugating by diagonal is now very good. We will always work with this diagonal group. We could work with another diagonal groups. Another diagonal groups is meant another what is called a Cartan subgroup, so A in the group theory is called the Cartan subgroup. And the fact that any reasonable matrix is diagonalizable tells you that modulo conjugation, that's what you are doing when you conjugate by a matrix. And that's what we really care. Now, there is a very specific subset of this A, which we fix forever in this course, which is A plus, which is called the positive cone. Again, you could choose whatever you want. The typical choice is what I'm doing, but this diagonal matrices, sum of T5 is 0, and you do T1 larger than T2. This is the positive cone, where you order the Ti's from the largest to the smallest. Okay? And then you see that if I conjugate by an element in this positive cone, then this Di minus Dj, if I'm in the upper triangular part, became positive, and if I'm in the lower triangular part, became negative. And I have to apologize because it would have been exactly the opposite as I said. I always have difficulties whether the upper triangular is I larger than j or I smaller than j. But it's one way or the other. Here is 50-50, not 90-10, but still let's agree that the upper triangulars are positive and the lower triangulars are negative. Okay? So in the exponent, which means that for the upper triangular, I'm multiplying by numbers larger than 1. For the lower triangulars, I'm multiplying by numbers smaller than 1. Okay? Now, here. Oh, we are essentially done. So let me, maybe this discussion. So this, what I just discussed, is the building block. What I plan to do next time is discuss a little bit of ergodic theory and dynamics, which are behind what we are going to say. And also I plan to do, which I plan to do today, but I end up talking too much about the groups. I plan to state the first main theorem we are going to prove in this course, okay? Which is very easy to state, not so easy to prove. Okay, so thank you. Sorry for the messy first day, but I will try to see if I can fix all this business or not. Okay, see you in 2 days. Bye-bye. Okay, now we are recording. Even though it will not be recorded what I said so far, but this is everything written here, okay? So let me clarify that, because we are going to play a lot with this action of G on G mod gamma. So this is left multiplication this G star is left multiplication by G, which goes in A group. You have the Gaussian space, and you can define this G mod gamma Gaussian space, homogeneous space, it's called homogeneous space. And you have this left multiplication. Sometimes you don't put star, not SG, you just write G times X times gamma, because that's what you are doing. Now notice that there is no right multiplication unless you are in nice situations, like very nice situations. You will not have a right multiplication on G mod gamma. Okay, because it's not well defined, you cannot go through gamma. So this doesn't make sense a priori. If you have normal groups or blah blah blah, then you start making sense of this type of thing. But in general, this makes no sense, so we don't do it unless we can do it. Okay, so this is multiplication. This is a nice space, actually. So just on general nonsense, you can put on it some distance function, which makes it into a metric space. Actually, the way you do it, I don't want to enter too much into this type of details, but you can put in G a distance, given a Riemannian distance, a Riemannian metric, which is invariant by right multiplication. And the fact that it's invariant by right multiplication on G, it makes that this Riemannian metric can be projected to G mod gamma. And then you have a Riemannian metric on G mod gamma. Or G mod gamma may fail to be a manifold, so actually you cannot really put a Riemannian metric on G mod gamma, because gamma may have, so the gamma action on G may have fixed points. That's especially true when you have torsion, for instance, or things like that. Okay, what I'm saying, the action of gamma on G, but actually the action of gamma on G is free, so because G is a group and gamma is a subgroup, so this is free, and the discreteness will come make this into a discontinuous action. So yeah, we are happy here. We can do further quotients and then it's a mess, but we are not doing these further quotients. So everything is nice. So this is a covering space. G is a covering space for G mod gamma. Then the distance essentially can be projected, and you get this nice distance on G mod gamma. But the distance in principle, and in this nice situation we are going to care, is not left invariant. And it's very important that it's not left invariant, because that's what makes the richness of all this theory. And so these maps LG, they are not isometries. Okay, if the maps LG were isometries, then you will have left invariant distances. Of course, for some G, it would be an isometry, but for the relevant ones, will not be. But yet, it could be that there is a measure which is invariant by all these elements. Now, it's not really hard to see that once this measure exists, is essentially unique modulo of the normalization you put here on this finiteness, and it's the projection of the Haar measure on G to the G mod gamma. Okay, so we have this projection here, phi from G into G mod gamma, which is phi of x is x times gamma. And the measure up here is not finite, so we cannot project it completely the measure here, but if we do it on compact sets, then everything is nice. It's very similar as what you do, and this is the very first example, even though it's not a very good example for what we are going to do next, but it's a very good example for this. So we put G equals to Rn, gamma equals to C to the n, and then we look at G mod gamma is the torus. Okay, here everything is nice because everything is abelian, so actually this guy itself is a group, and life is beautiful. Emotional situation, the quotient space is not a group. And here we have the fundamental domain of the torus, which maps, so the boundary, or the non-injectivity, if you want, has zero Haar measure, and once it has 0 Haar measure, it projects in an essentially one-to-one fashion from here to there. And this measure here, the Haar measure here, gives rise to a measure here, which will be invariant by translation because it is invariant by translation. And the same thing we have here. So in general, we have sigma, a fundamental domain, meaning that sigma times gamma equals to the union of sigma times gamma is equal to G, and sigma intersection sigma gamma is empty at every gamma infinite from identity. Okay, so that makes it into a fundamental domain, like the square here. I'm not giving yet, and we are not going to discuss unless it's really necessary, about the geometric properties of sigma. So here in this picture, this fundamental domain is the square. It's a beautiful fundamental domain whose boundary is these piecewise segments, which make it beautiful. In general, in higher dimensions, and even in the torus, you may have a very ugly fundamental domain being just some strange measurable set. Well, I want it to be measurable after all, but I don't really need much more to talk about the measures. Okay? Or later we will discuss something about nicer fundamental domain. They have even named the Dirichlet ones, especially. But so far, that's what it is. Now, more generally, there is a proposition which is not very hard to prove. I will leave it to you as an exercise, which says that if I have gamma is a subgroup and G mod gamma is compact, then gamma is a lattice. Okay, and this should be suggesting you that there are lattices whose quotient is not compact. So these are called non-uniform lattices. So when the quotient is compact, you sometimes call them co-compact or uniform, and when the quotient is not compact, sometimes you call them non-uniform. It's just a name, but the area or the volume of the quotient space has to be finite by definition. That's the main business over there. So let me give you an example of a lattice other than these co-compact lattices that so far I didn't give any explicit. For the type of groups we care, our main examples of groups is SL and R. Really want to hear about them, and the main example is SL. So this is a non-co-compact lattice. It's not really very hard to show. I again leave it as an exercise to you that this is not co-compact, so the quotient is not compact. You have to find a sequence of points that xn gamma goes to infinity, whatever it means. So what it means is not convergent. You can essentially make a sense of going to infinity. It's not really hard. And so it's not co-compact. Yet it has finite covolume. So G mod gamma has finite. And this is the theorem, essentially. So in this case is older, but the general situation is by Siegel, which is exactly that. We are going to show it, but later. Okay, it's a very important, non-trivial, but beautiful proof. And the proof goes through finding something very close to a fundamental domain, which has finite volume. And once you have a fundamental domain with finite volume, you are done. Okay, so instead of building a fundamental domain, we are going to build what is called a Siegel domain. And the Siegel domain is something that will satisfy this first condition, not the second, but this is enough to show the finite volume. It's a very explicit fundamental domain, and the computation of the finiteness of volume is not hard, it's beautiful, because it goes through understanding what is really the hard measure on this space, and that's very useful in general. Though we don't need it for what we are going to do first, but eventually it's good to know how to do. Okay, so these are lattices, and these lattices are very close to be the main object of this course. So understanding these lattices. Okay? So the first thing we are going to address is one old problem which was solved in the 70s, early 70s by Margulis, which is what are the normal subgroups of these lattices? Let's do the definition of lattice theorem. So let's concentrate in this group. So this is what is called a simple Lie group. And here simple Lie is to be taken as a joint adjective. So it's not a Lie group that is simple, it's a simple Lie group. Okay? So first definition of being simple. Now, I have to apologize, I always forget. So yeah, simple is what I'm going to read. I always confuse perfect with simple. But I think I'm correcting what I'm going to say. So G is simple group if it has no non-trivial normal subgroups. That's it. Simple group. Now, at least in odd dimension, SLNR has, in even dimension, SLNR has normal subgroup because plus minus identity is a subgroup, and it commutes with everyone else, so it's a normal subgroup. So certainly it makes that SLNR is not simple for n even. For n odd, it's actually simple, but we want to put all together, so a simple Lie group, is a simple Lie group if let me put the simplest definition, which is it has no connected, no non-trivial connected normal subgroups. So every normal subgroup is essentially discrete. And the equivalent definition would be, which is the most standard definition, is asking the Lie algebra to be simple, but then I have to define what is a simple Lie algebra. I don't want to spend the time now on defining simple Lie algebras, even though it's pretty much the same definition, but for Lie algebras. And we should discuss what is normal in the setting of Lie algebras, which are ideals. So an SLNR is a simple Lie group with this definition. So the only normal subgroups of SLNR are the total, the identity, and plus minus identity when it is a subgroup. And in this case, it's discrete, so it cannot be. Okay. So now the big question is, does this property, so is this property inherited by the lattices? So are the lattices in a simple Lie group also simple? Okay, and that's why the title is normal subgroups of lattices. So if we can say that there are no such normal subgroups, then the lattices will be simple. Now, we can go and discuss a little bit of SL2. It's a very special case of this SLNR. And this SL2R is pretty much related by the fact that if I position SO to R on the right, I get essentially the upper half plane. Which is the x plus iy such that positive. And this upper half plane is essentially the universal cover to any surface. Okay, particular to hyperbolic surfaces. Now, any surface of whatever genus will be the quotient of this upper half plane mod a lattice. And this quotient, so this genus to surface, for instance, is compact, so this gives you lattices here. One can go and find explicit examples of gamma. Is not really incredibly hard. It's not 100% trivial, but it's not impossible at all. And then we have lattices, which are essentially the fundamental group to this guy, to this genus to surface. And we know that the H1, the cohomology with coefficients in Z of this guy has two expressions. One is that it's isomorphic to Z to G, and that can be computed quite explicitly, putting, so knowing the pi1 of the guy, and actually that's what I should do, but let me not do it. And this is the same also. Now the second is essentially definition as homomorphism from the pi1 of Hg, some fixed point into C. Now this pi1 is, by the theorem of coverings, equivalent to gamma, because gamma is acting as deck transformation here to give you this quotient. This is simply connected, which means that the pi1 of the quotient space can be identified with gamma. And the fact that this homomorphism from here to here is C to G, it tells you that there is at least one of them which is non-trivial. So we take L from non-trivial, and we get that the kernel of L is normal subgroup of gamma, and we have a non-trivial normal subgroup. Okay? I have plenty of non-trivial normal subgroups. So even though SL2R is simple, the lattices are not simple and are very far from simple, so it has plenty of normal subgroups. Okay? So what Margulis theorem says is that when you go to larger n, this is not anymore the case. And that's the theorem. Theorem. Gamma is much more general than this. I will just state it in the easy situation. Easy to state, not to prove. Gamma lattice. N at least 3, because for n equals to 2, we saw that we have all these cases. Let n be a normal subgroup of gamma, then either n is a subgroup of the center of SNNR, which by itself is a subgroup of plus minus identity, so it has at most 2 elements, so it's a very obvious normal subgroup, or gamma mod n is finite. Okay? So which tells you that then n is almost everything in gamma. And in particular, n is also a lattice that can be seen easily from this B finite. Okay, so you have these normal subgroups here, which are, let me show examples of these normal subgroups appearing very naturally, the cofinite ones. I will show you them in a second. And that's it, because the other is just this guy in the center, and of course, if this center is the lack of the actual group to be simple. So G is not simple due to this center, essentially. And, well, what do you expect then? But outside from this center, you only have these guys. So that's the theorem, the first theorem we're going to prove. Let's see. Very important examples, which are called, if I remember correctly, congruent subgroups. So we call gamma n is all the matrices A in SLNR, such that A is identity mod n. Okay, and this actually, you can see easily that this is a normal subgroup because you have the natural map, how should I call it, phi to n from actually GL, but let's do SL, and whoops, should be a C because if I'm V mod n plus into some integers there into SL n z mod n z, which is this map. A is equal to A mod n. Okay, and then this guy is nothing but the kernel of phi n, so it's naturally a normal subgroup of this homomorphism, and the fact that it has, so in this situation it's very easy to see that this quotient is finite, simply because the image there is a finite set, is at most n to the power n. This is pretty much n to the power n up to some very small number. So in this very specific example, you have this. And what Margulis proof is that that are essentially all the examples. Okay, actually one can play a little bit with this theorem and really play a little bit and see that eventually this group N will have one of these examples as a subgroup. And so it's really, that's how they go. Okay, so the question now is how we prove this. And indeed, the proof we are going to present is not very far from Margulis' original proof. It's a little bit more symmetric than Margulis' proof, but it's still the basics are pretty much his own proofs. And actually, isometric interpretation of his proof, it comes from Katok's work, which also by itself has been inspired a little bit, but later works of Margulis on this type.
So I just have a question. So these are examples of what exact? So what is this example of exactly?
This example is a subset of a normal subgroup. So gamma n is a normal subgroup of SL and R. So these are guys that satisfy the hypothesis. I put R or C, Z. I keep on putting the other. So here I'm using as gamma. This is the lattice. So I have this normal subgroup of gamma, and of course it satisfies the theorem, so it's not a counterexample because the theorem is true. So the quotient is finite, but are examples which are not in the center, which are the other trivial examples. So these are not fun at all, but you have these other guys. And the point part of the interpretation as well of the theorem is that these, which are the main examples, are very close to be really all the examples. So nothing else. It's not really true that nothing else.
Why do we need n greater than 3?
The little n. Okay, so there are two reasons. One, which is not very deep, which is because if not you have a counterexample, or n equals to 2. But the second is much more important, which is we will see in the proof how heavily we are going to use the fact that n is at least 3. And I can say one more word about it. Was the principal consequence of this n at least 3. And actually we are going to be discussing this for the next 2 weeks. What's happened with this fact, before we really go back to the proof of this theorem. So, but the main thing is that, remember, we have this decomposition as being the compact A, which is diagonal matrices, and upper triangular ones in the diagonal, and these are positive entries, And the point is that this A here is isomorphic to Rn minus 1. And the main thing is not that n be larger than 3, but that n minus 1 be larger than 2. Okay? So this is very important for us. So we want to have two commuting matrices which are not the same matrix essentially. And for n equals to 1, for n equals to 2, n minus 1 is 1, and so you have just a one-dimensional Cartan subgroup. So one-dimensional. And that's the crucial thing. And we are going to understand a lot of the dynamics of these guys, of such A. Okay, so a good chunk of what we are going to play has to do with the dynamics on A on G mod gamma. And we want this not to be just a flow that when A is one-dimensional, we want this to have two commuting guys which are really independent. And that will start making the machine. So, okay. Now, let me stop for a second. And let me try to convince you of one basic property of these quotients of G, and try to see if I can convince you that understanding these guys will be very useful to prove this theorem. V be A times M. Okay, so we are still working inside SLNR. So we have these which are just upper triangular matrices. Positive entries in the diagonal. Is really not very important. We could add all the upper triangular matrices, simply then it will not be called P, but anyway. So, well, actually I should add them, and then it's actually P, but it's really not important for us. It's not a serious issue for us. So this is the group of upper triangular matrices, and we can consider the quotient. And then for first time, I will quotient on the right. Okay, it's not really important because you can always switch from right quotients to left quotients. I'm just quotient on the right because when this guy will appear in the middle of the proof, it will appear as a right quotient space instead of quotient. Okay, now imagine you have a group H.
So the cosets there are of the form PG, not GP. So what do you mean when you say quotient on the right?
Oh, is that when I do the equivalence relation here, so the elements here.
Are they PG or GP?
Is P times
Okay.
G.
Okay.
So these are the elements, which says that the equivalence relation is defined so that these are the classes. And then, of course, I have the group G acting in here by right multiplication now. Now, this P is not even discrete, but moreover, this action of G on G mod P, which I will try to make some pictures soon, has no invariant measure. And actually, most elements will not have an invariant measure.
But isn't the quotient here compact in this case, or?
I'm sorry. Yes, the quotient is compact. So yeah, individual elements will have an invariant measure, but when I try to make invariant by more elements, then I will not be able to do it. Okay? So, and there is no invariant measure which is invariant at the same time for everyone. We will see an example in very little, and it will come clear. Actually, I should go to the example now, but before doing the example, let me put as a question.
So that's essentially a flat manifold, no?
Yes, that's what is a flat manifold.
Okay.
And actually, yeah, maybe before putting the question, let me introduce this type of manifold just in a purely algebraic way like I did, without giving much of the geometric interpretation. So if I have any other Q that is contains P as a subgroup, then I can also do this quotient G mod Q, and I still have G acting on the right. Okay? Now, part of the game of asking P to be inside Q has to do with what Nawa remarked, is that this quotient is compact. And this quotient is not compact because I have P. So if I can guarantee that what I'm quotienting here contains this P, I will have that this quotient is compact. If I try to go smaller than P, then the quotient is not compact anymore. Okay, so this is like the smallest group I can take so that this quotient is compact, but to be serious in what I just said, I need to add a lot of conditions also. But that's pretty much why we play with this one. Now I can look at this G acting on G mod Q. I can look at the subgroup of H, of G, H. I can restrict to this action. And I can ask to myself, or maybe simpler, so if I call alpha this action, I can look at what is the kernel of alpha. Okay, the kernel of alpha will be arguments G in G such that alpha of G is identity, or equivalently and more explicit is the G's in G's such that Q times X times G is Q times X for every X. Okay, so this is a very explicit guide. It's not hard to see that it's a group. And, well, we can try to understand what this is. And part of the game will be to understand this. Now, let me describe who is this group in 5 minutes. Before, let's see examples of this boundary to have a geometric picture of what these G mod P are doing, and why I'm calling them boundaries. Let me show first why this G mod P is compact. Okay? And then I go directly to the very basic examples. So, as we said before, G can be written as K times A times N. And this decomposition is actually unique. It's not so important for what I'm going to discuss, but it's unique. So, I have any element in G can be written uniquely as a product of a little k, little a, and little n. Now, if you want by taking transpose or inverses rather than transpose, you can write it as well as n times a. Well, you have to take inverse if you really want to do it that way. N times a times k. And notice that n times a is still p, even though elements in n do not commute with elements of A, but N normalizes A. So then I can do it both ways. So which means that G is P times K, which means that G quotient by P is K. And what I'm writing like letters and divisions and multiplications actually can be formalized not very hardly as a very explicit map from K to G that I can quotient by P. Okay, and it's an onto map and then onto a continuous map, and hence it gives you the compactness of the G. Okay. So that gives you the compactness. Now let's do the example. Even though it's not really the case with here, let's still do the SL to R because it's really very good to understand. The SL3R will be pretty much similar, and SLNR as well. So what is the compact? Compact is SO to R, which is the circle. It's a one-dimensional manifold, the only compact one-dimensional manifold, so this is G mod P. And before I tell you more explicitly how you as well can identify G mod P with this guy, let me tell you how this action goes. G on G mod P. So you have three main guys here, K, A, and N. And notice that in this case, and actually it's also true in more general, these K, A, and N also separate three types of matrices up to conjugates. So the matrices in N has all eigenvalues 1. The matrices in A are diagonalizable. And the matrices in K are isometries. Okay? So this gives you the three main categories that you typically learn in linear algebra. And these three different categories will tell you that there are three different behaviors on this boundary G mod P. So if I take a matrix K, you will just rotate some angle alpha, which depends on what is the matrix. So K is rotation by alpha, and then you rotate some alpha there. Actually, there will be an alpha over 2 maybe, but again, it's not simple. Yeah? Let's not do this. So this is SO. Then the diagonal matrices, what we'll have is essentially two directions. One direction, which is this invariant subspace, the other direction is the other invariant subspace. So we will have these 2 points, and every point go, well, depending on what's the eigenvalues, so of the elements in A, go all from one side to the other side, or vice versa. That's how applying A does to these elements in G mod P. And finally, the N will act on the circle by having one fixed point, and then all the guys just go all the way around to here. And so to making these last three descriptions is better, instead of doing this, what I did, that the compact is isomorphic or homomorphic and diffeomorphic to G mod P, I will give a better description, which is not this G mod P as a circle, but as a projective space, a one-dimensional projective space. And then that's a better description, and it's much better to understand what happens with the matrices. And here, these matrices A, B is one of A actually, 0, and this is essentially RP1. Which actually is, on one hand, you can go and directly identify it with the extended real line, and that's the reason you call it a boundary, because this extended real line is actually the boundary of the upper half plane. So in this case, saying G mod P is the boundary of H, which remember, now I'm pushing in the other direction, G mod K, but again, this is a different interpretation. That. So what is RP1? RP1 is lines on the plane, okay, on R2. And I claim that each element here corresponds to a line in RP2. And how it does? Well, I have this guy. This guy I identified with the horizontal line. Then I have all these other guys, which I identified with a 1B element. And each of these guys has a unique class P times this element. Okay? So in this way I have identification of each vector 1B with an element in G mod P. I am missing only one element, which is the purely vertical guy, which is the class of P times 0, 1 minus 1, which is the class which I'm not counting here. And then I have this identification of this extended real line with this guy. And the point is that when I multiply this guy to this vector 1B, it is mapped into the corresponding line, which will be the, well, it's not the same B, but T. So you take the 1T, you apply this matrix, it will move to AT, which is T over A, and this is how the guys are moved. And then if I apply any of the matrices in SL1, the matrix is either linear, diagonal, or rotations, or the shearing. That's what I end up having here, which is either translation C plus 1 on this vertical line, which goes from minus infinity to plus infinity, and that's the fixed point there, or I have the guys going towards 0 and getting away from infinity, which is the two fixed points, 0 and infinity, or I have rotations, which is just rotation on this extent. So maybe it's also good to see what happens now for SL3. It's very similar.
First sort of time.
You have time? Yeah. Okay, actually, yes, we are 3 minutes late. Okay, so maybe we stop now, and next Monday I describe SL3, so what are these boundaries of SL3, and I answer. Well, this one I can answer. In this situation, we can answer it right now in 1 minute. So I wrote a kernel here. So this is, you can think of this as a little bit of abuse of language, because I never said that this alpha, so this alpha is an action, I'm not saying it's an homomorphism. So even though I'm talking about the guys going to identity, if it is not an homomorphism, it may not be really what we want to be a kernel, but actually, if you interpret it in the right form, alpha is a homomorphism, so then this is a kernel, and then it's a normal subgroup. And it's a normal subgroup of G. And a normal subgroup of G, we know what they are, because G SLNR is either everything or inside plus minus identity. And we can see that unless Q is all of G, it cannot be everything. So that's very easy to check. And that's what we are going to take here. So we are going to put this n here inside this kernel. And once we put this n inside this kernel, we get either what we want, or we get that this Q here is all of G. And this Q will have a very explicit geometric meaning. So the fact that this Q is all of G will give us a lot of information. Okay, so that's what we are going to do. Okay, thanks, and on Monday we continue.